Hello friends, today on behalf of Quantum University we are bringing the new course to cover quantum computing with Qiskit. So I am going to demonstrate entire process how to create a quantum circuit, how to compile it, and then I will also discuss a Little-Endian system followed by Qiskit. So first of all we need to install this Qiskit library. So as you can see, this is the tip command for installing the Qiskit library. We also need to install Qiskit Air. This is our simulator package, and Matplotlib. This will help us in the visualization of our quantum circuits. So just let me run this cells. While it is running, let me also tell you that our course will cover most basic to advanced, and currently I am dividing it into several chapters. Each video will bring you with certain concepts and experiments, and our Jupyter notebooks, it will be available for free download. It has run already. Let me now move to next cell. So here I am importing certain classes. This quantum register is a basic Qiskit class which creates qubit register, the quantum register. Classical register where the qubit measurement will be stored, and quantum circuit basically combines these two. So I am defining my qubit register at qubit. It is, for example, I am taking 3 qubits as of now. Let me change the comments. I am naming my qubits Q so that I can specify which qubit is the one on which I am working, and my classical register Siragit also has 3 bits and I am naming it as classical bits. After defining these two variables, I need to define the circuit. I am using variable name circuit, and this quantum circuit, the basic class, combines these two, the quantum register and classical register, to create a quantum circuit. After this I need to apply certain gates. So again we are following gate-bitch quantum computing here. Maybe in future I will also consider uploading videos on photonic or continuous variable quantum computing, but that is for later. Today I will now concentrate on gate-based quantum computing. So you are already aware of X gate, the C node gate, control X, control node gate, Hadamard gate. I am applying X gate on my 0th qubit, control node gate on the qubits 0th and the first one. And here the first one is the control qubit and the second one is the target qubit, that is the convention followed by Qiskit. And I am applying Hadamard gate on the qubit number 2. That is 012, that is the last qubit. I can now draw this MPL as Matplotlib. So if you don't use MPL, it will draw a simple diagram with lines and squares, basically very simple diagram, and using MPL gives you quite profound color scheme diagram. So let me run it. I show it. Yeah, so now you see my circuit is ready, and here there are 3 quantum bits, Q0, Q1, Q2. There are 3 classical bits. This cross line means these 3 bits are combined. So instead of drawing 3 lines separately, Qiskit draws all classical bits together. This is the X gate I applied on my qubit 0. This is C0 gate. Again, Q0 is the control bit and Q1 is the target and Hadamard gate which I applied on Q2. Now I need to run the circuit and see what state is the output of this quantum circuit. Before I run it, let me also mention that Qiskit follows 0 default initialization. That means all my qubits, the Q0, Q1, Q2 will be in state 0, gate state 0, before I apply any gates on it. So let me now run my simulator, and for doing this I am importing state vector simulator. Currently in this video I will concentrate on state vectors. Later we will go on other simulators too. In this state vector I am importing from quantum info. That has a special purpose because I want to show you my state in Browt that is in deduct notation. So from state vector simulator I am using run method and passing the circuit. It will give me something in output, I mean create a job. It is just in variable name and from job I can deduce the results and get the state vectors. Currently I am setting the decimal point precision at 3. Let us see what is given to me. So from this command, the print state is printing my state vector in array format. As you can see, of course the result is same, but it may not be easily readable. So for making it readable and slightly beautiful I am taking this input and converting it into state vector, which is a method available in quantum info. What state vector does? It converts my array in a proper format so that I can draw it in, for example in latex format. If you pass this latex setting inside, it will print it beautifully like this. So the output of the circuit is the state vector. And how Qiskit does this? In fact, just to clarify to ourselves, I will also go through hand calculation in my next video, but I want to mention one important point at this juncture, that is the Qiskit follows Little-Endian system. What does this mean? What is Little-Endian? Little-Endian system means this: the ordering of qubits is in such a way that the rightmost bit is the least significant. That means my qubit 0 is this one, qubit 1 is this one, and qubit 2 is this one. Same thing here, this rightmost bit is the least significant qubit 0. This is qubit 1 and this is qubit. I can in fact demonstrate it through a simple change in my experiment. Let me go to my circuit. Let me comment out these two lines. So now I have only x get the not get at qubit 0. Let me now read rather circuit. See, this is qubit 0. I am applying a state there. Q1 and Q2 I am not doing anything. Let me now run the simulation once again and see what is the outcome. In the meantime you can guess what should be the outcome. See, I have run it and this is the state vector and this is the state vector in proper latex format bracket notation. See, since I applied the sget at Q0 and Q0 the default state was 0. So after applying x0 becomes 1. And now it is 0 0 1. There is no coefficient here because this is the state is in itself normalized. There is no need for any coefficient. Now let me show you what happens if I apply xget in qubit number 1. So now I have applied in on qubit number 1. What should be the output you can guess. In the meantime let me run the circuit. See, these middle one, the qubit 1 has become 1. Because the application of xget, and just for the sake of complete test let me also apply xget onto at the time. See, now I am applying x at Q2 the last qubit and let me run the simulation. So now my Q1 has become 1. So this is the Little-Endian system. The rightmost bit is the least significant Q0 and the leftmost bit is the most significant whatever Q2 or Qn whatever it is. So with this let me now complete this video. I hope you found it interesting and useful. I will come back with my next video where I will show this calculation by hand. I will go step by step, take the different qubit states, apply the gates and show you what should be the outcome. If you like the video please like and subscribe and share. Thank you so much.